So good evening, everyone. It's so nice to see so many smiley faces. So we had buying the solution from weights and biases. We had an approach from building everything on our own. So it kind of reminds me of the Matrix with a blue pill and red pill. So what if I told you that there is a third option? Okay, so I'm Alexander. I work as a software engineer at Neptune. I haven't worked there for long, so I have Timek with me to help me with any questions that I might not be able to deal with other way. Good. So let's start. So I will begin, as is right, with a rather obvious observation that you will probably all agree with. There are so many machine learning powered apps and services nowadays, right? And you might say, wow, you're so observant, and it's good that you pointed out. But it actually has a lot to do with the presentation. So with so many machine learning power apps, it becomes overwhelming and very complex for engineers and practitioners to build and develop and deploy the models, especially at scale, right? So it might not be that pronounced if you have one or two teams that deal with it. You know, if it's just, two people hanging around and deploying models, and maybe most of the stuff that I want to talk about is not very relevant to you. But if you have 3, 4, 5, I don't know, 10, maybe hundreds of machine learning teams, and then, think about platforms, right? So what machine learning platform aims at is taking away some of this burden of engineering overhead, so that the complexities that might be there during the machine learning lifecycle can be reduced, and the teams are better enabled across projects and workflows. And it accomplishes it, or at least it aims to accomplish it, by standardizing the technology stack for your data. So it not only provides the tools for you, but it also applies the standard principles of MLOps, of engineering. So actually memorize a catchphrase to summarize this, and I really hope that I will not mess that up right now. Okay, so in summary, machine learning platforms take away the how from where, when, and how to build and deploy models. Okay, nice one. So there are two. If you decide that you don't want to build everything from scratch, you basically have two main approaches to it. You can purchase an end-to-end stack where you commit to one provider, and it solves all or maybe most of the things that you deal with in such a platform, in such a set of tools. But as you might guess, I'm not going to talk about this one. The title of the presentation is about building it from components, and that's the second option, where you don't commit to one provider, but you actually pick the most suitable provider for a given task. So for example, you have data validation components. So you pick Great Expectations. You have model registry or something, MLflow. Feature store, well, build it ourselves, right? Great. That's what we aim to do. And it's really hard to say which approach is better. It's actually probably impossible to say. It all boils down to your business model. How do you like to handle the granularity of the system? So the advantage of an end-to-end stack is that, first of all, you don't need to have many different skills with many different technologies, right? So you just have everything from, I don't know, data robot, and you just need to know how to operate on that. You don't need to know, well, okay, MLflow here, Great Expectations there, how to handle our own feature store and stuff like that. So in many cases, it might be actually easier, and there is much less friction between the components on the end of the day, right? because this is all just one provider. But there are cases for building an ML platform from components, and the key phrase here, is flexibility. Okay, so you can get very flexible in how you compose your platform. You can pick the best tool that you want for a given task. So let's say that I don't know. Let's say that I committed to one provider, but I kind of don't like how they do X components. In this component approach, you don't need to worry about that. You just pick a different provider for this particular component. So obviously the disadvantage, or maybe not a disadvantage, but rather a trade-off that you make for this flexibility is that there might be some friction, and you need to have more skills. Okay, and to this friction, I'm going to come back in a minute when I'm going to talk about what makes a good component of an ML platform. But first, let me briefly introduce Neptune. So Neptune actually provides one of the components for you. Okay, it doesn't handle the entire platform. It's the experiment tracker component. Okay, so how many of you use experiment trackers in your? I kind of figured that out. Thanks, Derek. So not many of you. Wow. So how many of you know something about experiment tracking, what it can be used for? Okay, that's good. So experiment tracking in ideal world probably wouldn't be that useful, right? But is the world ideal? Well, it ain't ideal, right? So we have bugs in the code. And I think that we can all agree that bugs in machine learning experiments are remarkably tricky to handle. Okay, because you have a lot of complexity, that's one thing. You have, hyperparameters, different parameters, stuff like that. You have maybe some randomness included. So it might get very complex very quickly. With experiment tracking, so this kind of this tool, experiment tracker, that allows you to track and store the metadata that revolve around your experiments, your machine learning experiments. You can actually make experiments reproducible. And there is an entire world of difference between debugging a reproducible experiment and debugging an experiment that is not that reproducible, right? So I think that we can all figure out which one is easier. What is more, experiment tracking also allow you to better collaborate, especially if you have different teams, but also within one team, okay? So you can share the results, you can compare your models. It's much easier to hand the models over later on, okay? You can visualize stuff, you can discuss it with a context already, okay? You have two different experiments that just differ with some hyperparameters. You can easily see which one performs better and get some insights from that. Okay, so as I promised, we're going to talk about what makes a good component of a machine learning platform. So as I mentioned, if you have an end-to-end platform, you don't have this friction, right? The tools work with each other perfectly, everything's fine. But if you have different providers, it might get tricky. So a good component needs to be easy to integrate with other components, because imagine if it is not easy to integrate. Recall that I mentioned that machine learning platform aims to decrease the complexity of machine learning systems. But if you have a platform that is comprised of many different components that just don't click with each other, does it solve this complexity? Or does it add more complexity on top of the existing one? Right? I think that, at least in my opinion, it doesn't solve the problem, or it wouldn't solve the problem entirely. So in order to make a component easy to integrate, you have to make it flexible and you have to make it simple. The API needs to be simple, because if it's not simple, it's actually very difficult to build integrations with other tools and libraries that you might want to use in your systems, okay? So we actually have a guideline at Neptune how to build integrations, and the primary point, the primary job of an integration is to save users time and enable them to write less code, okay? So someone wise once told me that good machine learning engineer, you know, they can love coding, it's fine, it's great if they like what they're doing, but they need to hate the code, right? Okay, so I hate the code. I want to have as little code as possible to get the job done. I hate having too much code in my projects. So this is the assumption. And another assumption is that if you are to write some code, then write the code that the user of the integration could write themselves. But they just won't have to do it, okay? We provide them. We provide them with this code. This point is a little subtle, but it's actually very important, okay? Because this way, if we only write the code that relies on our user exposed API, we make an integration much more robust. Because even if there are internal changes in our backend, the integration still needs to hold, right? We don't want to change the integration anytime we have a new backend release, right? It just wouldn't be a good model. So let me actually give you an example of one of the integrations. And this particular integration actually is very relevant to the talk. So ZenML, how many of you have heard about ZenML? Anyone? Well, actually, there are some people that heard about it. Okay, so it's a little niche, in my opinion, but ZenML is a framework for developing machine learning pipelines, okay? So what is exactly relevant to this talk is that those pipelines are made of components, okay? And you can, not only do you have different stack components, as you have here, okay, so orchestrator, step operator, model deployer, feature store, stuff like this, but each of the stack component has something called a flavor, okay? So experiment tracker, okay, so experiment tracker is a stack component, but it can have a Neptune flavor, or weights and biases flavor, or MLflow flavor, probably also Comet, don't remember. So I want to tell you that we love ZenML at Neptune. But the thing is that at the beginning, ZenML didn't seem to love us back. So I want to take a short detour from this presentation and actually talk to you a little about the challenges that we had developing this integration. Because I told you a good component needs to be easy to integrate, right? That doesn't mean Neptune is not a good component. This is to say that you will always get some challenges. And I think it's very interesting to see what exactly happened here and how peculiar the solution turned out to be. So the problem, it's not a problem per se, but from our perspective, the problem with ZenML pipelines was that they should not, by design, exchange state between the steps of the pipeline, right? And our friends from weights and biases had it much easier. You do, you know, this init, and then you just log the metrics. You don't exchange any objects between the steps. But this is exactly what we had to do. So our initialization returns an object to which we log the metadata, and guess what? This object isn't serializable yet. And the ZenML pipeline steps are meant to only exchange simple data. Okay, so some integers, maybe some strings. So not a suitable environment for integrating with Neptune, or so it seemed. And that's exactly why I want to talk about it. why this makes it so interesting. Because at the end of the day, we actually managed to overcome it. We used a mix of an approach that uses this dreaded singleton pattern that actually in this one particular case turned out to be a good point for implementing this pattern, and the functionality of, you know, fetching existing runs using a custom ID that could be exchanged between the steps. So it was very tricky, but thanks to, you know, close collaboration with this NML team, we eventually managed to overcome it. So I encourage you, if it's interesting for you in any case, check out NML and check out the examples of using Neptune and other integrations in those pipelines. So at the end of the day, we actually managed to succeed, and that's all that counts. And we still keep on developing new integrations, and we try to support new tools to make a machine learning practitioner lives easier and their work more manageable. Okay. So now the dreaded moment, the moment I've been dreading for a while. So if anyone feels like humiliating a junior developer is something that you need to do right now, then now is your time. No, I'm kidding. Just if you have any questions, I will be happy to try to answer you.